Assalamu alaikum. That is lecture 1 for week 4 for the subject microprocessor programming and interfacing. Course code is CS430. Before we start today's lecture, we have to take a quick review of the previous week lectures. In previous week lectures, we have an introduction to the instruction set of 8086 8088 microprocessors. Then we divided the instruction set into different groups of instructions, and we completed discussing data transfer group of instructions, and we started discussing arithmetic and logic group of instructions during previous week lectures. During this lecture we have to cover some subgroups of arithmetic and logic group of instructions. So first group we are going to cover in this lecture is ASCII arithmetic instructions. So first instruction is ASCII adjust after addition instruction. Purpose of this instruction is to adjust the result within AL and that will be converting back it into unpacked BCD form. So instruction format is AAA, and when this instruction will be executed, if the lower nibble of AL is greater than 9 or auxiliary carry flag is 1, then 6 will be added to AL and higher nibble of AL will be cleared or will become 0, and 1 will be added to AH if this adjustment is done. Otherwise, if adjustment is not required for the AL, then 1 will not be added into AH. And both auxiliary carry flag and carry flag will be set after the adjustment is made. Other flags will be undefined. Second instruction within this group is AAS instruction, ASCII adjust after subtraction. So that instruction will be correcting or adjusting the result present within AL after subtraction of two numbers, two unpacked BCD numbers, and that is the format AAS. During the adjustment, if lower nibble of AL is greater than 9 or auxiliary carry flag is set, then 6 will be subtracted from AL, and if this and the higher nibble of AL will be cleared or will become 0, and 1 will be subtracted from register AX. Auxiliary carry and carry both flags will be set to 1 if the adjustment is made. Remaining flags will be undefined. So here we are having some examples for A instruction and AAS instruction. So that is first example. We have added 3436, that is equivalent to 4 and 6. 34 is the ASCII for 4 and 36 is the ASCII for 6. So we are having 46 within AX, and in AL we have added 38. So here we are going to add 46 with 8. So that is the calculation. In AX we are having 34, 36. We have added 38 with that value in AL. So result will be 346E. Now when AAA will be executed, ASCII adjustment after addition will be executed. So there is E within the lower nibble of AL, so that is requiring the adjustment. So 6 will be added with E and you will be having 4, and the higher nibble of AL, that is 6, will be resetted or will be cleared to 0, and as the AL value for AL is adjusted, so AH will be added with 1. So 34 plus 1, 35. So after execution of AAA instruction, AX will be having 3504. Now we have to convert the value of AL from unpacked by BCD form to ASCII form. For that we have added 30 with AL. So result is 3534. So we have performed this addition. 46 plus 8 equivalent to 54. 5 ASCII for 5 is 35, ASCII for 4 is 34. So in AX you are having 35, 34. In example 2 we have subtracted 38 from 34, 36. So 34, 36 is equivalent of 46, and from AL value we have subtracted 38. So AX will be having 34FE. After the subtraction instruction, AX will be having 34FE. Now for adjustment we have used AAS, ASCII adjustment after subtraction. So AAS will be checking the lower nibble of AL, that is E. So that number is requiring adjustment. So 6 will be subtracted from the lower nibble of AL. So E minus 6 equivalent to 8, and the higher nibble of AL will be resetted or cleared to 0. And as the adjustment is made for AL, so 1 will be subtracted from AH. So 34 minus 1, 33. Now that is the value in AX after AAS instruction. Now we have to convert the unpacked BCD present within AL to ASCII. For that we have added 30 with AL. So your AX will be having, after addition of 30 with AL, AX will be having 33, 38. So that becomes 38. 33 is the ASCII for 3 and 38 is the ASCII for 8. So 46 minus 8 is equivalent to 38. We have performed this calculation within processor, and we have adjusted the result by using AAS instruction. Now another example. Here we are having 34, 39 within AX. That is 34 is the ASCII for 4, 39 is the ASCII for 9, and we have added 38 with AL value. So that means 49 is added with 8. So in AX, after addition of ASCII numbers, we are having 3471, and when this calculation will be performed by processor, auxiliary carry flag will be having logic 1. So for adjustment of the ASCII to back to the ASCII, we have used AAA instruction, ASCII adjustment after addition. So as you may see that lower nibble of AL is having 1, that is not requiring the adjustment, but because of auxiliary carry flag is having logic 1, so AL will be adjusted. For adjustment, 6 will be added with the lower nibble of AL. So 1 plus 6 equivalent to 7, and the higher nibble of AL, that is 7, will be resetted, or that will become 0, and 1 will be subtracted from 1 will be added to the value of AH. So 34 plus 1, 35. So that is the value 3507 within AX register after execution of AAA instruction. Now we have to convert 07, that is in unpacked BCD form. We have to convert this 07 into ASCII. So we have added 30 with AL. So 07 plus 30, 37. So now you are having 35, 37 within AX. 35 is the ASCII for 5 and 37 is the ASCII for 7. So that is the calculation. 49 plus 8 equivalent to 57. Now we are having another example for subtraction AS instruction. Here we are having 34, 31 within AX. So that is the ASCII format for 41. 34 is the ASCII for 4, 31 is the ASCII for 1, and in AL we are having 38, that is the ASCII for 8. Now after subtraction instruction, AX will be having 34 FE, 34 F9. After subtraction instruction, in AX the value will be 34 F9. So, and auxiliary carry flag will be having logic 1. So when AAS will be executed, that will be checking the lower nibble of AL, that is 9, not requiring adjustment, but because of AF, auxiliary carry flag is 1, AL will be adjusted, lower nibble of AL, from the lower nibble of AL, 6 will be subtracted, so 9 minus 6 equivalent to 3, and higher nibble of AL will be cleared to 0, and as the adjustment is made for AL, so 1 will be subtracted from AH, so that will become 34 minus 1, 33. Now in AL we are having unpacked BCD form number. We have to convert it back to ASCII form. For that we have added AL with 30H. So 03 plus 30 will be 33. So in AX we are having 3333. So 33 is the ASCII for 3 and 33 is the ASCII for 3. So 41 minus 8 equivalent to 33. So that is these are the examples for ASCII arithmetic instructions AAA and AAS. Remaining two ASCII arithmetic instructions are AM instruction and AAD instruction. AM is ASCII adjustment for multiplication, but the purpose for this instruction is to convert hexadecimal number into unpacked BCD form number. So that instruction converts the result of multiplication into two BCD digits into unpacked BCD form. So what will be done during the operation of AM instruction? Contents of AL are converted into two unpacked BCD digits and those digits are placed in AX. So contents of AL are divided by 10 decimal or A hex, and the quotient will be moving into AH register and remainder of this that division will be moving into AL register. So in the coming slides you are having an example that will be clearing that operation. Next instruction is AAD instruction, ASCII adjustment for division. So purpose for this instruction is to convert unpacked BCD form number in present in AX into hexadecimal form, and that is used to convert dividend within AX into hexadecimal form before division. So what will be the steps? The unpacked BCD operand present within AX is converted into hexadecimal or binary. AH will be multiplied by 10 and then the value will be added with AL and AH will be cleared after that addition. So an example is coming in this lecture for explaining AAD operation.
Now we are having an example of division of two unpacked binary BCD numbers. So dividend is in AX, that is in ASCII form 3837. So that is the ASCII of 87. 38 is the ASCII for 8, 37 is the ASCII for 7. In BL we are having 33, that is the ASCII for 3. So we have to convert it into unpacked BCD form. So we have subtracted 3030x from AX, so that will become 0807. Now we have to subtract 30 from divisor, so subtract BL comma 30x, so that will be converting BL into BCD number 3. Now we are going to perform subtraction. Before we perform subtraction, we have to convert the dividend into hexadecimal number, or you may say binary numbers. For that we have to write AAD instruction. So AAD will be multiplying AH with 10 decimal and will be adding the value of AL with that value. So you are having 8 in AH, so that will be multiplied by 10, so that will become 80, plus the value of AL is having 7, so 80 plus 7, 87, that is decimal value will be present within AL after execution of AAD instruction. Now the value present in AH will be cleared, so AH will be having 00 after execution of AAD instruction. So 0087, that is the decimal value present within AX. And if you see this value in hexadecimal, that will be 0057 hex. So that is the operation of AAD instruction. We have converted AX value into hexadecimal by using AAD instruction. Now we are going to divide AX by BL register. So div BL will be dividing AX by BL, and quotient of this division will be moving into AL, and remainder of this division will be going into AH register. So 87 decimal divided by 3 decimal, quotient will be 29 decimal, or otherwise if you see the value of AX register in hexadecimal, so your dividend is 57 divided by 3, so quotient will be 1D hex, and that will be present within AL. So that is the quotient of division. Now remainder of this division will be 0, as 87 is perfectly divisible by 3, so there will be 0 remainder. So 0D or 0 hex, same thing, so AH will be having 0 as remainder. Now we have to convert back value present within AL into unpacked BCD form. So we are going to use AAM instruction. So that will be the calculation behind the AAM instruction. Value present within AL will be divided by 10 decimal. If you see the value of AL in decimal form, so AL is having 29 decimal, that will be divided by 10 decimal. So quotient of this division will be 02, that will be moving into AH. If you see AL in hexadecimal form, that is 1D hex, that will be divided by 0A hex. Quotient of this division will also be 02, that will be present in AH, and remainder of this division will be moving into AL register. So 29 decimal divided by 10 decimal, or otherwise 1D hex divided by 0A hex, remainder will be the same, that will be 09 present within AL after execution of AAM instruction. Now your result is in unpacked BCD form. AH is having 0209 in it. So we have added 3030x with AX value. So you will be having 39 and 32 and 39 within AX after execution of add instruction. Add AX comma 30 hex. After execution of this instruction, AX will be having 32 39x. So AX is having ASCII of 2 and 9. 32 is the ASCII for 2 and 39 is the ASCII for 9. So your answer is 29 decimal. So if you divide 87 decimal by 3 decimal, you will be having 29 decimal. So that is the answer present within AX register. Now we are going to discuss rotate instructions. In rotate instructions, uh, there are two operands. First operand on which the rotation will be performed, and second operand is the value how many times we are going to uh, perform rotation on the first operand. So a table is given for showing the different combinations of D and count. So D may be an 8-bit register or a 16-bit register or a byte from memory or a word from memory. Count may be 1, or if you want to mention count greater than 1, you have to use CL register for that. So that is the case where you are using 16-bit processor. In case of 32-bit processor, more than one count may be mentioned in the instruction, like 2, 3, 4 may be written after comma, but that is the case where you are using 32-bit processor. For 16-bit processor, if you want to mention more than one count, you have to use CL register for that. You may not write directly count greater than 1 in the instruction. Now we are having some examples. The operation of ROL. So in ROL, D will be rotated left without carry flag. Rotate left without carry flag. So MSB of D will be copied into carry flag, and MSB of D will be copied into LSB of D, and the D will be rotated left. In case of RCL, rotate left with carry flag, MSB of D will be copied into carry flag, and carry flag will be copied into the LSB, and register or memory whatever is present as D, that will be rotated left. In case of ROR, D will be rotated right without carry flag. So LSB of D will be copied into carry flag, and that will also be copied into the MSB of D, and D will be rotated right without carry flag. In case of RCR, carry flag is to be included into the rotation operation. So LSB of D will be copied into carry flag will be copied into the MSB of D, and D will be rotated right in such manner. So these are the rotation instructions. Now we are having some examples for rotation instructions. ROL, rotate left AX without carry flag one time. ROL AX comma 1. So 1 is the count, AX is the register on which you have to perform rotate left without carry flag operation. Now RCL, rotate left with carry flag on DH register one time. So the first example you are having 16-bit register, in second example you are having 8-bit register. So both are correct. Both may be performed within ALU of 808 806 microprocessors, but count is here 1 here. So only one time that rotation will be performed within ALU, and result will be in the same register. Now ROR BT1 comma 1, and BT1 is a byte within data segment, and that is having 8E data. stored at BT1 location. So that 80 hex will be rotated right without carry flag one time in ALU of processor, and the resultant will be stored back to the memory at location BT1 within data segment as a byte. So that is the rotation, right rotation on memory one time. Now we are having ROR WD1 comma 1. WD1 is a word within data segment and having value 30F0 hex. So that word will be fetched from memory, and one time right rotation with carry flag will be performed within ALU, and the result of that rotation will be stored at WD1 location within data segment as a word, and that is the complete operation of this instruction. Now ROL DX comma CL. So DX registers contents are to be rotate left without carry flag CL times. So whatever number is present within CL, that is the count, and for that count we have to rotate left DX register without carry flag, and result will be stored in DX. RCL BH comma CL. So BH will be rotated left with carry flag CL times, and result will be stored in BL. ROR byte pointer within square bracket 200 hex comma CL. So a byte is fetched from 200 offset within data segment, and that byte will be rotated right within ALU CL times. Then the result of that rotation will be stored as byte at location 200 within data segment. That is the complete operation for this instruction. Now ROR word pointer 300x within a square bracket comma CL. So a word is to be fetched from 300 offset within data segment, and that word will be rotated right with carry flag within ALU, and the result of that rotation will be stored back to memory at offset 300h within data segment. So that is the complete operation for this instruction. Now we are going to discuss shift instruction. There are 4 shift operations: shift left, logical left shift, arithmetic left shift, logical right shift, and arithmetic right shift. In instruction format, there are 2 operands. First operand is the operand on which we have to perform shifting, and second operand is having count, and the combination of the D and count are shown in the table. These are the same combinations we have seen for rotate operations. So SHL and SAL both are having same operation. D will be shifted left, and a 0 will be inserted in LSB, and MSB will be shifted into carry flag. So that is the complete operation for logical left shift as well as arithmetic left shift. In SHR, 0 is inserted in MSB, and LSB will be shifted to carry flag. So that is the operation for logical right shift. In case of arithmetic right shift, no 0 will be inserted in the MSB, and MSB will be maintained, and right shifting will be performed. LSB of D will be moving into carry flag. So that is the operation. For we are having examples for shift instructions. SHL AX comma 1, shift logical left AX one time. So AX will be moved to ALU. There you will be shifting AX one time, and result will be stored back to AX after shifting operation. SAL arithmetic left shift DH comma 1. So DH is to be shifted arithmetic left, one time within ALU and result will be stored back to DH. So 8-bit operation here. Now SHR BT1, 1, so that is logical write shift, and a byte will be fetched from memory that is stored at BT1 offset within data segment, and that byte will be shifted right one time. After shifting, result will be stored back to memory at BT1 location within data segment. SAR WD1, 1, so word will be fetched from memory within data segment present at WD1 offset, and that word will be arithmetic shifted arithmetic right within ALU, and that result of that shifting will be stored back as a word at location WD1 within data segment. Next example is shift left dx comma cl, logical left shift dx cl times whatever number present in cl, that is the number, that much time dx register is to be shifted logically left, and result will be stored in dx. SAL BH comma CL, so contents of BH are to be arithmetically shifted left within ALU CL times, and result will be stored back to BH. Now SHR byte pointer within square bracket 200 hex comma CL, so a byte is to be fetched from offset 200 within data segment, and that byte will be shifted left CL times within ALU, and result of that logical write shift will be stored back to memory at the same address within data segment. Now SAR word pointer 300 hex within square bracket comma CL, so a word is to be fetched from 300 offset within data segment, and that word will be shifted arithmetically right within ALU CL times, and result of that shifting will be stored back to memory as a word at the same offset address within data segment. So that is the complete operation for these shift operation. Now we are going to discuss flag control instructions. So we have discussed flag control instructions earlier for interrupt flags and direction flag. So here we are having some instructions for carry flag, some instructions are for interrupt flag, and some instructions are for direction flag. So carry flag may be assigned logic 0 by using CLC instruction, clear carry flag. After execution of CLC instruction, carry flag will be having logic 0. After execution of STC instruction, set carry flag instruction, carry flag will be having logic 1. Then you are having CMC instruction, complement carry flag. So carry flag will be inverted if carry flag is having logic 1 before execution of CMC instruction. So after executions, carry flag will be having logic 0. Or otherwise, if carry flag is having logic 0 before execution of CMC instruction, after execution of CMC instructions, carry flag will be having logic 1. Now you are having two instructions for assigning logic 0 or 1 to interrupt flag. CLI, clear interrupt flag. So after the execution of CLI instruction, interrupt flag will be having logic 0. Then you are having STI instruction, set interrupt flag. After the execution of STI instruction, interrupt flag will be having logic 1. Now there are two instructions for setting and resetting direction flag. If you execute CLD instruction, clear direction flag, that will be assigning logic 0 to direction flag. Or otherwise, if you want to set direction flag, you have to execute std instruction, set direction flag. So after execution of std instruction, direction flag will be having logic 1. Now we are going to discuss data size conversion instructions. So there is an instruction cbw, convert byte into word. So before execution of cbw, you will be having a byte in al. After execution of cbw, that will be the value present within al will be sign extended and will be converted into ax. cwd instruction is used to convert a word into double word, and same concept is here. You will be having a word before execution of cbw within ax, and cwd will be extending the sign bit, sign of that number present within ax, and that number of 16 bit will be converted into a double word, that is 32 bit. Lower 16 bit will be stored in ax, higher 16 bit will be stored in dx. Now there is another instruction for 32 bit processors, cdq, convert double word into quad word. So you will be having a double word within EAX register. During execution of CDQ, sign will be extended for EAX register, and a 32-bit number present within AX will be converted into 64-bit number. Lower 32-bit will be stored in EAX, higher 16-bit will be stored in EDX. Now we are having some examples for CBW and CWD. So that is first case, that you are having 69 hex within AL, sign bit of AL is 0. So after sign extension in AX you will be having 0069 hex. So a byte is converted into a word by using CBW instruction. Now you are having a byte in AL 94 hex, sign bit of AL is 1. So after execution of CBW instruction, AX will be having a word, that is FF94X. So sign bit is extended and AH is having the sign extension of the number 94X, and 94 is present within AL. Now third example is having AX 40F6X, sign bit of this number is 0. After the execution of convert word into double word instruction, CWD instruction, result will be within dx ax register. So as sign bit is 0, dx will be having all zeros. So your 32 bit number will be 000040F6 hex. In fourth example, we are having a 32 bit number within ax C236 hex. After execution of CWD instruction, that will be converted into a 32 bit number double word, and that will be stored within dx-ax. So as the sign bit of ax is 1, so all the bits of dx will be 1. So you will be having FFFF within dx, and ax will be having C236x. So these are the data size conversion instructions.